Okay, here we go. Luke Skywalker.
Oh, wait.
Start there.
Yeah. Hey, there you go.
Good job. So Luke Skywalker. So we got most of the way on this one through the difficult parts of it. I think the kind of the key, of course, was understanding. I think if we had just started from scratch on this one, it would have been much more difficult. But hopefully, and what I was hearing in your groups, I think a lot of good discussion, of realizing you do this, and some of it came after some prodding from me, some hints from me, and so forth. I think some of the things I spent the most time talking about in the beginning, especially, I talked about the why was it like a Shanghai type problem, and so we know how difficult the Shanghai type problem was back in the beginning, but we know it's something like this, and we're looking at it was trying to go to a spot down here, so there's some tangent line. Essentially, we don't know this, we do know this, and so where we still run into trouble, I think, is people recognizing what those equations mean in a parametric equation, right? I mean, it's the horizontal and the vertical position, but in any graph, that's what the x and y coordinates are. In the Cartesian coordinate system, right, which is what that's called when we do x and y, right? Everybody heard that before? No? Okay. That's funny. Your AP calculus seniors have never heard that before. That's the fault of our math department, I think, for never using that term. But it's something that actually over time we've gotten less formal with our language, I think, mathematically. And that's one of the things that probably falls by the wayside. It was named after a famous philosopher, French philosopher, René Descartes. And he was a mathematician, philosopher, and so forth. And it's named after him, the Cartesian coordinate system. So we have x and y. Now you might say, well, are there other coordinate systems? Well, there's the polar coordinate system. Did you do anything with Mrs. Payne with polar coordinates? I think she used to, but I'm not sure she does anymore. I always think of when in Calc 2, you get into some polar coordinate stuff. A polar coordinate system is, okay, so if I have this dot right here and I want to name where that is, the Cartesian coordinate system, sometimes called the rectangular coordinate system because it's right angles, x's and y's, and a lot of cities are mapped out this way, right? Your streets all run vertically or horizontally, right angles to each other. But the one I was thinking was like a radar tracking planes. That's in a circular kind of a situation. And so this point right here would be, in a rectangular system, you give it an x coordinate and a y coordinate, right? Horizontal, vertical. In a polar coordinate system, you would give it an r and a theta. So it would be how its location would be determined by what angle is it from there, and then how far away on that angle is it. That'd be the radius. And so the coordinates of that would be given by an r and a theta. Okay, so you think about it, well, it makes sense. You could name any point anywhere out here. It would be a certain rotation and a certain distance away from some center point. Anyway, I digress. That's another type of coordinate system. So when we're doing parametric equations, though, we're talking about x and y values. And so we're talking about just a point in the xy plane, and these are equations that give us the x and the y. So I had the question come up yesterday. Somebody said, well, in the Shanghai problem, we had y equals 1 minus x squared. And so when we had the point x and y, we just substituted this in place of that. And I had somebody say, so what would we do on this one, right? How would we do that on this one? Because we don't have an equation like this. Well, and then the realization came, yes, we do, right? What did we substitute for this y here? Yeah, we put that in. Not only did we, in the Shanghai problem, because we were in the using functions, x and y type equations, we just substituted this for the y, and we didn't substitute anything for the x, and then we had everything in terms of x. But in this problem, people soon realized that we're actually going to substitute both of those, right? The x can go there, and the y can go there, and now we actually have this equation in terms of t. All right, so when you were doing your, slope between 2 points, right, then the realization at some point, it took a while for some groups and longer for some than others, but the realization was for y, you can put that equation, and for x, you can put that equation, right? Anywhere you see an x in these problems, it represents that. So anyway, and then of course we wanted to, that's the slope of this red line, and then we wanted to set that equal to the other version of slope we have, which is y prime over x prime. So y prime over x prime had t's in it, this had t's in it, now it's just an equation to solve. And another thing that struck me is several of you were not quite grasping what to type into your calculator for solve, and I realized that we have spent so much time, almost every equation we've solved in here has been what? Equals zero, right? Derivative set equals zero. Then I think some of you almost thought every equation you ever solve has to be equal zero, right? That's not the case. Right, you got something equals something. That's your equation, right? And you just put it in like that. There were some people trying to somehow get an equal zero out of that. And so we, couple of things that I noticed as we were working along. Anyway, once we got to there, we recognize that once we find that time then, where he's there, we got everything we need. We got everything we need. Now it's just a matter of plugging in stuff. So when we go to here and we look at this, okay, we know what time he was there. So if we know what time he's there, we can plug that into here and plug that into here, and that gives us the x and y coordinates of this. Once we know the x and y coordinates of that, and we know the x, y coordinate of that, we can find the distance through the distance formula. And how far away was he? Like 3 point something? 3.1 something, right? Was his distance away from there? Okay? And then we can find his speed, right, at that time, because we know the time, so we can plug a time into x prime and a time into y prime and plug it into this, and we can get his speed. And if we know his, and so if we know his distance, if we know how far away he is, and we know his speed, then we can simply divide distance divided by speed and get the time it takes him. And it took him less than 3 minutes, I think, right? Was it 3 minutes? It took him less, so he makes it. He makes it, right? And so that was about all you had left to get to. But again, the hard part of that problem initially would have been getting that set up and understanding how to find that time. Once we had the time, it was pretty easy. Right, because then we knew the point, we knew the distance, we knew the time, we could find all those things, or the speed. But recognize, so the lesson there is recognizing it was that Shanghai situation, right? So when that comes up in the future, right, that's what we're hoping for, that we can recognize that we got a tangent line on a curve. This happened to be a parametric curve, but most of the time for us it's going to be just a normal curve, a function curve. Recognize it's a tangent. We don't know where it's tangent, but we do know another point. 2 ways to do slope. Set it up, solve, and we can find then where it's tangent, and then do whatever else the problem needs. Okay, let's move on to the book problems. Let's start with the swimming pool problem, which was number 26, I believe. That was the one I had people in here this morning asking about. That was probably the most difficult one to set up here. But we could look at some of the other ones as well. While we're getting that. Okay. So now it said it wanted to know how fast was the water. So the pool is filling up. How fast is the water rising when there's 2,000 cubic feet in the pool, and when there's 3,000 cubic feet in the pool? Right? Those are the 2 questions, right? So let's address the 2,000 cubic feet in the pool. So in my picture, as the water fills up, the problem becomes, where is the water when there's 2,000 cubic feet in the pool? Some of you know this already because you were in here this morning. Well, where is it? It's down in the bottom, right? Now, how do we know that? Well, we know that because we can figure out the volume of this triangular wedge. How do you find the volume of a triangular wedge? Length, width, height divided by 2, right? Because the triangle is half the base times the height, and then you also have the width. So in this particular picture, be 7 by 40 by 15, and then divided by 2. So 7 times 40 times 15 divided by 2, and I think that's 2,100. So what that means is the bottom wedge piece is 2,100 cubic feet. So when there's 2,000 cubic feet in the pool, that, now what would I label that? The 2,000. Volume, right? So that tells me the volume is 2,000. Let's go ahead and write down the other things I'm told here. What else was I told about this problem? There was a 25 in there. What was that? So what would I label that? V prime, right? The water is coming in at 25, was it 25?
Yeah. Cubic
feet per minute. And then, that was it, I think, wasn't it? Is that all they told me? And then, so that's not very much, right? Not very much information to plug in. And then I'm trying to find what? How fast the water's rising. So call that H, I guess. So I'm looking for the height of the water. Now let me go ahead and draw the water in here. So the water, at this point in time, the water would be something like this. I like how I made that blue even. Works. Okay, so there's the water, right? The water level is down in that triangular wedge because there's 2,000 cubic feet at this particular time. So I've got some changing quantities. Now these quantities aren't going to change. The 40 across here, the 15, the 3. Okay, but now for the water wedge, this part is changing. So I'm going to put an H there. What about this distance across here? Is that changing? Okay, so what should I label that? You tell me. Length, okay, L. Right? And then what about over here?
No.
Is that changing?
No.
That's not changing actually, is it? That's 15. That stays 15 the whole time. So in that blue wedge, right? So I need the volume of the water. So the volume equation, what's the equation of this blue wedge here then? 15 L H divided by 2, right? So I'm going to write it this way, 15 halves L H, right? There's my volume. Okay, so, I mean, not terribly difficult at this point, although, you know, it depends how comfortable you are with geometry and being able to draw that picture and see that, you know. So you had to be able to, you know some basic geometry formula there to be able to find that volume, that kind of thing. But otherwise, not too terribly difficult yet. Not as easy as a simple right triangle, Pythagorean theorem, something like that, obviously. But a rectangle, right? Those would definitely be easier. But now, and this is just from having done a lot of these problems. Well, you guys tell me. What would? And I know somebody this morning said the same thing. What would be your next step? What's that? And I think I did, didn't I? I mean, the 15's not changing. The L and the H are, right? You know what I mean? So I think I'm at that point. Yeah, I think I've plugged in everything that's not going to change it. So in the list of steps, what's next? Do the derivative with respect to t. Now, I'm thinking ahead here a little bit. If I do this derivative, what am I going to have to do? Product rule, right? Which is fine. I can do the product rule. And when I do that, I'm going to have some L primes and some H primes and a V prime. Now, V prime's okay because I got a number to plug in. H prime's okay because that's what I'm trying to find. But do I know an L prime? I don't really know an L prime or an L, and you know, I don't have any of that information. Now, does that sound familiar? Did we do a problem yesterday where that happened?
Yeah.
Where we had some extra stuff. What was it? Which problem was it? The cone problem. Remember the cone problem? It had R's and H's and V's, right? And so we went ahead and did it, but But then how did we handle that? Where did we get that extra information from? Remember we had that other equation that was R equals 2H? Remember that? Do we have something like that here? Do we have some way that we can relate L and H? Look at the picture now. Do we have some way to relate L and H? Now you guys over here this morning don't say it. Over here? Now to me that would just add another variable, and I'm trying to get rid of variable, right? Anybody? That's okay though, good thought. Look at this blue triangle right here.
2H equals L.
Where'd you get that?
Yes.
Oh, okay. Caleb, what do you think? You see anything with this triangle right here?
Similar to the
Isn't it similar to this black one right here? Don't we have similar triangles right there? So what could I write? Caleb, keep going.
40 over L is equal to 7 over H.
Or I could have done 40 over 7 is L over H, same thing, right? But the corresponding part. So 40, which is this length, over L, is equal to 7, this black length, over H. That is true. And now we could multiply, that'd be 7L equals 40H, right? And then what can I do with that? What did we do with that yesterday then? Well, we could solve for one of these, but then when I do my L primes and H primes, couldn't I do the derivative, do the derivative of this too, right? And that would give me some L primes and H primes and things I could plug in, right? That would do it. But then what's the other thing we did on that cone problem yesterday? What we thought was simpler. We subbed in, right? We solved this and we subbed in. Now I agree, I think I would solve for L, because which one of these do I not really want to be in there? The L or the H? I don't really want the L to be in there. So really the key to this problem is seeing this relationship right here. Now in the cone problem, it's easier to see that relationship because I've already told you every cone problem has it. And usually in the problem, it says something about the radius and height connection. It'll say the radius is always twice the height, or it'll say the radius is 4 and the height is 16. Well, you know that that they have that relationship then. Here they didn't say that in the problem, so you had to see it. You had to see it. So now we can substitute that in. So we're going to get V equals, now, so we'd have 15 halves times 40/7 H, times H. Right? So I put that in place of L, so that would be, 300 over 7, H squared. Did I get that right? I think that's right. So that'd be 300, so that's better. That's better. So the key was recognizing these similar triangles. As that water rises, that triangular wedge of water is going to be proportional to the bottom section. Now we can do our derivative. So V prime is going to equal what? 600 over 7 H prime. Now I can start plugging in the stuff I know, right? I know 25 for V prime. I got 600 over 7. I need something for H, and then I'm going to find H prime. Okay, so what do I put in for H? Oh, I don't see anything up there for H. What do I have, though? What do I have that I haven't used yet? V is 2,000. What can I do with that? Can I put it right there? Can I put it right there and solve for H? A lot of times in these problems it'll say, how fast is the water rising when it's 6 feet deep at the deep end, right? Well, then they would have told us H is 6, but they didn't. They told us how much water was in the pool. But if we know how much water is in the pool, we know what the height is, right? We'll know that. So we'll just put the 2,000 right there. So let's solve that. So we got 2,000 equals 300/7 h squared. So go ahead and solve that real quick. You could just solve it on your own. Times by 7, divide by 300, do the square root, or you can do a solve. I don't care, whatever. Give me a exact number unless it's really a mess. Anybody else get 2 square root of 105 over 21? Over 21.
Over 3.
Poor Emily up in front. Man, we don't record. 2. That's what you didn't get your calculator out, did you? Because you didn't want to. So 2 square root of 105 over 3. You know, one thing you do have to be careful of on these calculators, when you hit divide and then you divide again, sometimes if you bring back the previous answer, sometimes it divides another time that you weren't supposed to. It sounds to me like you divided by 7 maybe one extra time somehow. And that's how your bottom turned into a 21. So what was it? 2 square root of 105 over 3. Okay. All right. And so now we want to solve for h prime. You can just get a decimal. That's fine. Okay. But so if I was doing this, I would have, a way to do this would have been 2, what is it? 25 times 7 divided by 600. Am I doing that right? 25 times 7 divided by 600 times 3. It's kind of a silly way to do this, but I'm just doing 1 at a time. Divide by 2, and then divide by, I'm hitting enter each time. What was it? Square root 105. Is that looking familiar? Anybody getting that? On then we do have to square. No, that should be it, shouldn't it? Oh, see, there's a mistake right there. Yeah, I think, what's that? Yeah. Now, see, I did the same thing I was just talking about there. What I was doing is I would hit divide by 2 and times by 3 and whatever. And what that does is grab your previous thing you did and do that. And so when I got to here, this did 7/16 divided by square root 105, which is this. And then when I hit Control Enter, what it did is redid the last thing I did. So then the last thing I did was take the previous answer and divide by square root 105. So when I hit Control Enter, this is a danger when you go to a decimal answer. When I hit Control Enter, especially if you've been doing multiple steps, when I did Control Enter, it said, okay, redo his last thing. Well, his last thing was to take his previous answer and divide by square root 105. So it divided by square root 105 again. And that's why that decimal's not right. But I think this thing is right. So what I need to do is I need to go up and grab this. I need to grab this, hit Enter, and then do Control Enter. There we go. Is that what you said? That's not what you said yet. Anybody getting that? Okay, I think this is right.
I did it wrong.
I think this is right. 0.043. Okay, but now, I mean, that's a little. Maybe you're better off doing the solve. I mean, it's kind of bad if we have our calculators in our hands and we have kind of a simple little algebra kind of thing we have to divide and we don't do it. Right. That would be points that you would be a little upset about losing, right? So it's just about getting this over to the other side, right? It's multiplying by the reciprocal, whatever. You know, I kind of did it one thing at a time, but make sure we can do that. So anyway, it was 0.043, and I don't remember what the units was. This feet per minute. Okay, that's what we would come up with there. So it wasn't really anything out of the ordinary other than this recognition right there of that similar triangle. That was hard. That was hard to see in this problem, for sure. Okay? All right, let's look at some of the other ones here. What else? Any others in the book here before we go to the business packet? I can't remember what the book went for. Why? Yeah.
23.
On 23. Was that the one with the cone? Oh, yes. Yeah. This is, there's a hard one. This one's difficult. Again, there's one part of this that's difficult as well. A little out of the ordinary. But again, that's the whole point of this week, right? The whole point of this week, Macy and I were just talking about at the beginning of class, that we've said all along, getting these things set up, right? And every problem's kind of a new thing. But there's not an endless supply of different new things that you can have, but there's a lot of them. So we're spending days working on them, and every time a new one comes up, we say, oh yeah, if you see this, do it. Now, hopefully we do enough of them that you can, most of the ones on the quiz, and that's my plan. My plan is most of the ones on the quiz should look similar to ones we've already done. Now, there might be one that, at least in one, where there might be something added to the problem. It might be a little different than we've done to see if you can come up with that. That's part of what you need to be able to do. Not just repeat things you've already seen me do. That's a big part of it. But, be able to adapt and use it on your own as well. So on 23, it's a cone problem. Is it like a cone, like a water tank kind of thing? So it'd be this kind of a cone. Okay, so anytime it's a water tank problem, that kind of thing, it's this kind of cone. If it's sand or something pouring down, making a pile, then it's an inverted cone. Actually they call this an inverted cone, but whatever. Okay, that's a cone, the other one. All right, but the thing they told you here, the thing they ask you for is what makes this one tricky. Okay, so they give you a whole bunch of information. They say water drains out at 10 cubic centimeters. So what should I call that? V prime, and it would be negative 10. Okay, so we need that. Then it says the depth of the water in the cone is 8. When the depth is 8, so that's changing. Of course, we got water here, and the water's draining out. Okay, so it's going down. So at the time when the height is 8, so that'd be H, it's decreasing. The height is decreasing, right? So what would that be? H prime, and it would be negative 2, right? And then, okay, so that's all that stuff we need. So we know what's the volume of a cone again? 1/3 pi r squared H, right? Now, normally, in a normal cone problem, in the one we did yesterday, and in most of them that you know, what other information do we have about the cone? The height and the radius. Somehow we know that relationship, right? We had one yesterday, the radius was always twice the height, so we knew R equals 2H, right? Or they just tell you that in this particular tank, the radius is this and the height is this. So you know the size of the tank, so that would give you that ratio. But what we have here is we have H and we have R, and as the water drains out, it's going to stay in this same ratio. So normally they give us that. Well, here it's kind of backwards. They are telling us to find that ratio. Okay? Well, really the secret to this problem is giving that a name. Was it radius to height, or is it height to radius?
Height to radius.
Height to radius. Here's the secret to this problem, is give that a name, and since it's constant, now this is important, the rate H and R are changing, but the ratio of H to R does not change, right? That's what we've been saying. Because of the similar triangles, the ratio of height to radius never changes. Okay? So that is going to be a constant. So I'm going to just call it K. So what I'm trying to find in this problem is that K. That's what I'm trying to find. Okay, so with that said, can't we make a substitution up here? Like we did before? If H over R equals K, wouldn't that mean H would equal RK? And could I substitute that in? Now we got to think about this though. What do I want to be in the volume equation, and what do I want to go away? I want to keep H, right? Because I got H information, so I want to keep H. I want to get rid of R, right? So I better do this the other way around. So I better solve for R. I better do this, right? So I better get R by itself, and now let's make that substitution right there. So now we get, so it's similar in what we do. In a cone problem, we have our 1/3 pi r squared h, but we usually don't want to keep both r and h in there. So luckily in a cone, we always know this information about the cone where we can make this substitution, like r equals 2h. Well, in this one, we don't have that information, but we do know that the ratio is a constant. So being able to set up this equation or thinking about doing that was the difficulty in this one. Okay, that was something you hadn't seen before. But now that we know it, look what we get. We get 1/3 pi. In place of the r, I'll put h over k. That would be squared, and then h. Okay? Now, put that all together and tell me what that would equal. Take a minute here to simplify that, put that all together. Tell me what would be a really good way to write it, because what am I going to do next? Do the derivative. So put that on, because this is a problem. Sometimes I think I do this too much for you and don't let you do this because then you mess it up. Do that. Put that all together in a nice form that would be ready to do the derivative. Cameron, what do you got?
B equals 1/3 pi times h to the third times y to the negative 7.
Times what?
Oh,
K.
yes. Okay.
K to the negative second. Okay? What you wrote is, okay, you said 1/3 pi h cubed k to the negative second. Right? Now, I agree with that, but I don't agree that that is in a nice form ready to take the derivative. Now, let's talk about doing the derivative here. The way he's got it written here, when we do this derivative, let me ask you this. When we go do the derivative, are we going to do a product rule on that? See, I disagree. Would we do a quotient rule on that? I disagree. Tell me why we would not need to do a quotient or product rule on that. Has to do with what k is. Remember what I said a minute ago? K is a constant, just like the 3 and just like the pi. And where do we like to have constants when we're multiplying, when we're going to do the derivative? We like them out in front, don't we? Right? So recognizing that k is a constant is really important here when we do the derivative. So now think about where we should put that. And I don't like the negative power either very much. So let's gather all the constants out in front. What would you have? Pi over 3k squared times, wouldn't it be h cubed? How you write things, when you're going to do the derivative, how you write them is critical for how hard or easy the derivative will be. Now, that's just rearranging, right? I mean, that's just algebra and rearranging. Now, we did have to recognize that k was a constant, right? But we run into these problems, and when we're reviewing for the midterm, we'll run into problems that have k's or a's, and they're constants. And we got to understand when we do the derivative, we treat those as constants. Okay, so now I'm ready to do the derivative. So that constant's just going to hang out there, right? Bring the 3 down. We'll cancel that 3. And now we're in great shape, right? Now we're in good shape because we know h we know H prime, and we know V prime. We know everything but the K. And that's what we wanted. So we got negative 10. I say we're in great shape, but I just got done saying how we sometimes mess this up, even though this should be, so this would be H squared, and then this would be negative 2. Okay, now you guys give me the K, right? I'm not going to just, sometimes on these problems I've been stopping here and saying, oh, okay, now you can finish it. And I'm not sure you're always finishing it. I think sometimes you just stop and you don't go back and finish it, right? So we're going to take time to let you finish this one. See what you have for K. It would be negative. It would be negative. We throw out the negative. Okay. So we're getting square root of 5 pi over 5. So are you doing just a solve? I mean, Tilda up here, she just did a solve and just typed it in just like that. So if you're nervous about messing up, doing something, multiplying something, do that. Yeah, you put it in just like that, do a solve, right? Okay, 8 square root of 5 pi all over 5. Now you want a decimal, that's fine too, right? Give me 3 decimal places if you want. But remember, what is that now? What did we just find? Well, yeah, I know it's K, but I mean, the ratio of height to the radius. The ratio of the height to the radius. Okay, so that was a little bit of an unusual problem because of normally a cone problem, they somehow in the problem tell you the ratio or the relationship between R and H, and that helps us to substitute here. Okay? All right. And then what were the other problems? 12 and 16. 16 was more of just a normal cone problem. Okay, the answer, let me give you the answers at least to this because I do want to give you some work time here. So the answer to 6, oh my goodness. What are you supposed to find H prime for 16? Is that what you were finding, the rate that the height was changing? Oh my gosh. Here's what they have. 1 over, somebody better put this in their calculator to see if 10 cube root of 9 pi. Now cube root would be, on your calculator, the best way to put that in is a 1/3 power. So 1 divided by, what was it, 10? And then 9 pi to the 1/3 power. Getting what you have? Okay, that would be the answer as a decimal. Okay, and then 12 was, part A was negative 1.5 inches per minute. The side would be, the height of the triangle would be decreasing at 1.5. And then what was the other question? Is the area increasing? And I think they got 7 for A prime. Is that the area? Really? No? Okay. We got a right triangle. What did it tell you on number 12?
The length of the
There sure were a lot of confused looks when I said that, so that bothers me. What's it say? The base is increasing at a rate of 2 inches per minute. So if I call this B and H, such a way that the hypotenuse remains. This is the ladder problem. This is a ladder problem, right? The hypotenuse remains 10 the whole time. So is this slice? So what you have is this is increasing, and this is decreasing. So the ladder's falling down the wall, right? So B squared plus H squared would equal 100. Oh, but we didn't have a problem with that one. Did you guys agree with that one, part A? Okay, so it was the area one. So the area of this is what? Right? And they're both changing, so we can't do anything with that. And so the area derivative, we'd have to do a product rule. So 1/2 B prime, H left alone, plus 1/2 B left alone, H prime. And then didn't they tell us all these things? They said, what was B prime? Was that negative? No, that was positive. That was 2. H we'll have to figure out here in a minute. What was, and then what's H prime? H prime was didn't it? Oh, we found that in the previous problem.
Yes.
At the same time, the height is decreasing in such a way that the length, when the length of the base is 6, so we know B is 6, right? So we can put that in. So we can put 6 in there. Okay, so if you have 6 here, what do you get for this one then? 8, right? Do Pythagorean theorem and you find that that's 8. And then H prime we found in the previous problem. And that was negative 1.5. Kind of run out of room here. So 16 times 1/2, that's 8. That'd be 3 times, that'd be negative. Oh, that doesn't seem right. That looks like 3.5.
Yeah.
Okay. Well, no wonder you look confused. Oh. Oh, they forgot the divided by 2, yeah, here at the end. Yeah, so 7/2. That's what happened. So I was going to say, all their numbers look the same as ours. Yeah, they just forgot the 1/2. So 3.5. So it's positive, so the area is increasing. Okay. All right. So, business packet. Okay, so 21, I'll answer questions individually on 21. I gave you that one because it was just like 19 and 20 yesterday, and then I showed you kind of a good way, a way to work those. So you should, just follow that. It's exactly the same thing. But 23 was a little different. 23 was a little different. So we've got this picture. So so we want to run this cable. This is like what does this problem remind you? The guy in the snow, right? The guy in the snow. It'd be a lot easier to lay cable on a power line on the land, not over or under the water in this case, but it'd be shorter if we went underwater, but it's going to cost more to go underwater, right? So how should we run it? Okay, so the key is setting up your distances here, okay? So you got 0.5, you got x. What you need to do is this right here, right? So that would be the square root of 0.5 squared plus x squared. That would be the distance on that, okay? And then the distance on this is, you can see it here, 6 minus x. Okay, so now so what we're trying to do, it says write a cost function. Now a lot of times we won't do that. Usually what we would just say is estimate the value of x that minimizes the cost. So step 1 is, what am I trying to minimize? Well, that's cost. So I got to write a C equals equation, right? That's the first thing I want to do. figure out what I'm trying to minimize, and write that down. So C equals, well, what's the cost? Well, it's how much per foot times the number of feet. So over land, it's $6 a foot. So 6 times 6 minus X. That's how many feet I'm running it on land times $6 a foot. And then plus $8 a foot times how many feet in the water, which would be the 0.5 squared plus the X squared. Right? There is my cost equation. So when we talk about setting it up, right, getting above the red line on the thing, that's where we're at right there. That's what you got to do to set that up. Your cost equation. All right? And then, now it said use a graphing utility to graph your, I mean, I don't care if you did that or not, whatever, you don't have to. And then it said estimate the value, so I don't know if they thought you could just graph it and then just trace, and maybe you did that, but that's not what we're going to do on the quiz, right? I didn't even recognize that they had said that in there. Really, what I want you to do is same thing we've always done on these minimum problems. Do the derivative, set equals 0, find your list again.
Would there be a problem with the $6 and $8 being per foot and the 6 and the 5 being in miles? Or is it...
No, heck, we can just ignore units, doesn't matter. There would be a major problem. Thank you, Rachel. There would be a major problem for doing that. Now let me think. Yeah, it's going to affect the numbers for sure. So how would we fix that? Just leave it. Yeah. I'm not telling you. You got to go back through the T's. Did I do that on my answer? Did you look at my answers? I did this right. Well, somewhere I must have adjusted. Oh yeah, I did at the end. But is that okay just to do that at the end? I multiplied by 5,280. Boy, that's a really good question. I should go back and tie that in. I don't, because that was my initial thought just now. Is would that matter in finding the? Boy, you would almost think it would. Well, no, I don't think it would, because think about this. What would that mean I was going to do? I would have to, this would be dollars per foot, and this would be miles. Let's think about this a second. I probably already thought about it, but now with my dementia, I probably forgot about it. But so the equation I have right now is dollars per foot times miles. Right? So how would I get that into dollars? I would have to times by feet per mile, right? And then that would cancel miles and cancel feet, and then I would have dollars, right? So how many feet per 1 mile? 5,280. So I would have to take this entire equation times 5,280, right? Which means this number and that number. Now let's think about doing the derivative. When I do the derivative, if I have a constant, because that's what I'm going to do next, right? So I got a constant out in front of all of this. What does you do with a constant? You just leave it hanging out there while you do the derivative of this, right? So you'd have this 5,200, so your C prime would have this 5,280 sitting out there times this derivative, which is the derivative I did on my answer sheet, right? And then I'm going to do that derivative and set it equal to 0. And so now when I get ready to solve this, what can I do with that 5,280? I got 5,280 times all this equals 0, so what can I do with this? Divide both sides by 5,280, which would still be that. And so now when I set that equal to 0 and solve it, I'm still going to get my same x values, right? So, in a sense, it doesn't matter that I didn't convert those. Now, I wouldn't practice that normally, right? Normally, I think I would want to do that. I think I probably realized it when I made the answer key when a smart student like yourself brought that to my attention. I said, oh yeah. And then I probably went through and said, okay, it wouldn't really matter till the end. So the X value you're going to find is going to be the same, but what will matter is that X value, which tells you where to do the station. It says, what is the value of X and minimize the cost? That's all you really need. But if you want to know the cost and you were going to plug it back in, if you plugged your X back into your cost equation, if you didn't multiply by 5,280, your dollars wouldn't be right. So from that standpoint, it would certainly matter. But finding the X value, it does not matter. But thank you for pointing that out, because you certainly want to pay attention in a problem with units that all the units are matching. Okay? And if they don't, if I give you the quiz and I say, hey, be sure to look at your units, that might be a hint that might be happening. I might point that out to you. All right, so there you go. So here's what we're going to do today. The rest of the time, I've got a parametric type problem for you to work on. You can kind of take your pick here of things to do. We're going to have a couple of days plus the weekend to be reviewing these things. So I'll show you. I've got another packet to give you from another textbook. It's got a mixture of optimization and related rate problems. So it's kind of your, I guess, study guide, if you will, over the course of the next 4 or 5 days. How do I do it? There it is here.
What's the test again?
Monday. So, this packet is, need another one? This is the famous Anton packet.
Anton.
I don't know why it's famous, but many calculus classes that have come before you will fondly remember the Anton packet. Probably not. They don't remember any calculus, but they remember the Anton packet. All right. So this is from another textbook that was written by a guy named Anton. So that's why it's the Anton packet. Okay? And so the first, now you notice these are from completely different chapters, which is interesting in this particular book. Why they would have been separated so far apart, I have no idea. I'm tempted to not even tell you which problems are which, because you should be able to just identify them. Okay? But you've got some circled problems on the first 2 pages. They are from exercise 4.6. Now it actually says up at the top what they are. But it should be obvious just reading the problem. Keep in mind, when you do number 1 and number 2, and number 1 and 2 especially. Now look at number 1. It says, let A be the area of a square whose sides have length x and assume that x varies with time t. Draw a picture of the square with labels a and x placed appropriately. B, write an equation that relates a and x. C, use the equation part B to find an equation that relates dA dt and dx dt. You see what I mean? This is like number 1 in their book. They're assuming this is like the first problem they've ever done of this, right? And so they're trying to lead them through the steps. That's what that's all about. So really, in problem number 1, you really only need to do D, right? That's really the problem. A, B, and C is just the setup of the problem. So, okay? So anyway, you've got those problems, and then you go to the next couple pages, exercise set 6.2, and there's some circled problems there. Those are the optimal. Oh. Okay? So what I would suggest, now tomorrow I'm going to give you a few optional ones that you could add to the ones that are circled here. But what I would suggest is you do a few of the ones on the first page, few related rate ones. Oh. And then on the next couple pages, do a few of those, right? Now I am going to give you some additional ones tomorrow, so if you got through all of them, of the circled ones, that'd be great, right? Leaving yourself some to do tomorrow over the weekend to continue to review would be good. And then here's a parametric, right, with the arrow. So that's not a bad one. Then I'm going to give you another parametric that you can do for practice tomorrow as well. Okay? And I've got the answers to this are going to be up on our website. And I've got them I've got a printed copy here of the Anton packet answers. Okay, so rest of the time's yours to work. And here's the business packet answers if you're still wondering about number 21.
I have
Oh, no wonder they were one short.
best barbecue grill in
Hey, is everybody's arrow problem a front and back?
Yeah.
I wonder I was one short.
one day. Boom. See, that's what I'm saying. You were as close as me to baby, and now you're like,
Sorry. Maybe next week.
yeah, next week, we'll all do it. Alright.
Are there any of them have answers to I think he said they're online and. Oh.
So, some of that paragraph, some of our reason is that, if you will, I didn't get any part of it. It was just like at first I felt busy,
Yeah.
hardcore, and I'm like, and then I started comparing it to Christianity, and I was like,